Hi, here we are discussing about a project implementations of high precision MFCC feature extractions using FPGA for speech recognition. So here audio recognitions is one of the technology that may be used for biometric identifications, and it offers higher applications possibilities in many sectors. At the moment, the implementations of the audio identifications algorithms on the hardware is mostly dependent on the SoC of the FPGA, and FPGA based real-time technique for extracting acoustic characteristics in the presence in the research. This method is based on MFCC, which stands for Mel Frequency Spectral Coefficients. The trial has shown that the FPGA based MFCC calculations has a high level of accuracy. The purpose of this study is to enhance the performance assessment of MFCC by making use of novelty based architectures. So in this study, a technique for FPGA based speech recognitions is provided. The approach was developed by the investigations and analysis of the audio recognitions algorithm, the FFT, the MEL filter, the DFT, the dynamic features derivatives, and the Hamming window and pre-emphasis are very aspects of this approach. The proposed MFCC final output will be present with the AHB interface in order to facilitate a higher access DMA controller when it is used in SoC applications. Okay, this work was carried out using Verilog visuals, and it is generated with a Xilinx Vivado FPGA. Additionally, all the parameters were analyzed and compared with regards to area, delay, and power. Okay, so now we can verify the work and the architectures. Okay, so here you can analyze this architectures. This is a proposed architectures. Okay, so here we are given an audio input, and that audio input given to the audio buffer. Okay, so it's processing the data with create some delay, and the pre-emphasis. Okay, and after that the Hamming window. Okay, so we can verify this block wise in step by step. Okay, so as per this architecture of MFCC proposed method, so we have used some reference paper. Okay, so this is a reference papers we have used. Okay, so here one is a low latency modular level deeply integrated MFCC feature extractions. Okay, and this one is a MEL filter, and this one is a hardware implementations of MFCC feature extraction for speech recognitions on FPGA, and this is another one reference paper for speaker verification. Okay, so here this is a main paper. Okay, so here you can analyze it. Okay, so here they are given the pre-emphasis window, FFT, and MEL filter, DCT. So all the components they are analyzed it. Here the pre-emphasis is the starting part of the after the audio buffer. Okay, so what here we are doing means here the pre-emphasis will sample the previous value and it will be subtract with the current value. So using this process of YFN, okay, it will reduce the most of the glitches in the input signal. Okay, so glitches or jitters, anything occur. Okay, so it will reduce it. Okay, and here they are multiplied the A value into 0.95, okay, to the previous value of. It's a perfect one for emphasis higher frequency. Okay, so after that the pre-emphasis output given to the Hamming window. So Hamming window means so here they are given is a Hamming window. It's same like as a filter. Okay, for this filter, how we are approached this means so here we are created a window with support of MATLAB. Okay, so here this is a FDA tool analysis. Okay, so based upon this filter design analysis, okay, we are created a band pass filter. Okay, so that filter order we are taken as a summon filter order specific adder, and the band pass filter will created the FS sampling frequency equal to 48 kilohertz and FC. Okay, so that is a first cutoff frequency, and FC2 is the second cutoff frequency. It's allocated the range of 20 to 20,000 hertz. Okay, and here also we are generated the coefficients. So as per the coefficients we have created a Hamming window. Okay, so here, okay, after this Hamming window the FFT model will be created. Okay, so it's a Radic 4 FFT. Okay, after that the MEL filter we have created. Okay, so here, so this is a MEL filter. Okay, so this is a MEL filter architectures. So as per the multiple number of frequencies, here we are used the multiple number of FIR filters. Okay, so that filters output come with the final additions in the MEL frequency system. Okay, so here as per this MEL frequency, so we have created a proposed architectures. Here we are given an audio input signal is 20 to 20 kilohertz. Okay, so as per that we have splitted the frequency with the FIR filters. Okay, so 5 kilohertz we are splitted. Okay, so here after the FFT output we need to split with real and imaginary. So we have used a real part and also for imaginary part. So here the 4 FIR filters we are used, but actually we are used a 8 FIR filter with real and imaginary part. The final additions we have come up with the MEL frequency. Okay, and the each FIR filters also designed with the same FPGA tool based coefficients created with support of MATLAB. Okay, so those are the screenshots. Okay, so after this MEL filters we have developed a DFT and the derivatives. Okay, so here this paper will support for the FFT, MEL filter, okay, and the DCT, so energy, the final energy part, and this paper also support for the energy. Energy means it's great the boosting the input signal. Okay, so they are x square the value. Okay, so this is called as a energy spectrum. Okay, after that this is the final. Okay, so derivative features. Okay, so this is equations we have used. Okay, so this is a workflow. Okay, so here in the coding part, okay, so this is a test bench of the coding. Okay, so here initially start with 2 clock signals. Okay, so one is for testing, another one is for real-time clock. Okay, so here real-time clock we have generated at 48 kilohertz. Okay, so it will be commanded because it will take more time for execution, so that it will be commanded. Okay, so and this clock we have used, it's a 100 Hz clock. Okay, so verifications. So here in the command line we have mentioned all the thing. Okay, so why we are choose the 48 kilohertz. Okay, so it's a professional based audio frequency systems, and high resolution means 96 kilohertz and MFCC equal to 40 kilohertz range. This range anything we can use. Okay, and after this clock generations, okay, so we have created a audio signal generations. Okay, this is an encoder. Okay, so we have used multiple number of input sound wave. Okay, input sound wave 1 2 6. Okay, so this hexadecimal file we need to read using the file reading code. Okay, that purpose we have created the audio signal generation. Okay, so this code will read the value. Okay, so which one you are needed, you can command or uncommand it. Okay, so here I will open it input sound 4. Okay, so this sound signal we are open it. Okay, so after this input generations we are coded a top model. Okay, so top model is MFCC feature extractions. Okay, so here you are used import clock reset audio enable. Okay, audio enable audio data come from the audio signal generation. Okay, so these are the input, and HR data H ready, and MFCC is the final output we are taken from the after the energy signal. Okay, and H address and H write data H write. Okay, so this is the AHP data. Okay, so here we have created some notifications of verifications code for ASB slave. Okay, and this is the top model. Okay, so here top model start with a audio input. Okay, so this audio input we are given to the audio buffer. Okay, so it will processing buffer and it's creating a delay. Okay, after that it will be given to the preamplifiers. Okay, so the preamplifiers already we discussed. Okay, so here we have used this method. Okay, so here so in the preamplifiers we have created a constant value of 0.95, and it will be used a multiplication part, and the subtraction part also we have used it here. Okay, so for multiplication process we are used as a array multiplier. Okay, so we are used a 8 cross 8 array multiplier, and also for 32 cross 32 array multiplier. So not used any operator, or not used any core generator, IB core multiplier. Okay, and this multiplier will support for signed and unsigned configurations. That's why we have used this multipliers. So internal architecture of this array multipliers, we have created a signed and unsigned configuration. So this is a 8-bit multiplier. Okay, so here we are created, okay, signed and unsigned configurations. Okay, so if the signed negative bit means we have taken a 2's complement, and output part also we are taken as a 2's complement. So we will get a signed and unsigned configurations. Okay, because here the signed multiplier is a more priority one. Why? Because we are always given an audio signal for this MFCC, right? That's why we have used the signed multiplier. Okay, after this preamp access we have used as a Hamming window. Okay, so this preamp access output. Okay, so we are given to the Hamming window. Okay, so this window part, it's a filter. Okay, so we have given the coefficients, and we are filtered it. Okay, after this Hamming window, the total factor memory we are used for FFT. Okay, FFT core generator. So this FFT core, it's a Radic 4 FFT. Okay, it's a 16-point FFT. Okay, so here we are used data input real and data input imaginary. So this two input we are given. Okay, with support of splitter. It will split the value. Actually here input we are given 16-bit. Okay, so this 16-bit we need to sample with number of times. Okay, after that we will get a x0 to x15, and the imaginary part x0 to x15. Okay, the real and imaginary we need to split it. Okay, so then the input signal given to the FFT core. Okay, so this is a FFT core. Okay, so once we are given, it will produce the output. Okay, so this signal it's helpful for time domain to frequency domain. Okay, so inside of this FFT core, we have used a Radic 4 butterfly architecture. Okay, after this FFT, the data out real and data out imaginary given to the MEL filter. Okay, so here the MEL filter will receive the data, and as per the architecture. Okay, so here we are shown one architecture, right? That architecture based. Okay, so this architecture but the MEL filter was designed. Okay, so here the MEL filter. Okay, so this is a MEL filter architecture, and after this MEL filter output, the MEL data, it's again given to DFT. Okay, so here the FFT will support for time domain to frequency domain. Okay, that frequency we are given to the MEL filter. Okay, and after that the frequency to time domain conversions will occur in the DFT part. Okay, so here the DFT process the data of MEL audio real and imaginary, and it will provide DFT data real and imaginary. Okay, and this data we are given to the dynamic feature extraction. Okay, and parallelly the Hamming output BF bandpass filter output given to the energy. Okay, and finally we are taken as a output. Okay, so this dynamic feature derivatives will work as this equations. Okay, so it's multiplications. Okay, with the imaginary part. Okay, so here sine means real and cos means imaginary. Okay, so once it will be multiplied, okay, so we will taken as a same output. Okay, so that is as MFCC data. Okay, so this MFCC data finally given to the AHP slave. Okay, so AHB slave will process this data. Here we are created a one state machine. As per the state machine, it will be work. Okay, okay, and it will process the data. Okay, and next thing is simulation. Okay, so here we have two set of simulations. Okay, so one is for input sound wave 1 and input sound wave 4. Yeah, input sound wave 4. You can change it and you can give any signal, otherwise you can download it any signal and you can give it. Okay, and so this is one of the part. Okay, so here you can analyze it. So this is the audio input. Okay, and this is the MFCC feature extraction top module. Okay, so here this is a Hamming window. Okay, so here you can analyze it, the filter of the Hamming window bandpass filter. Okay, and after this the frequency given to the FFT output. Okay, so here this is the FFT output. Okay, okay, so frequency domain output. Okay, and the MEL filter. Okay, so this is a MEL filter output, and this is a DFT. Okay, you can zoom it and you can analyze it. Okay, so DFT, you can check the output. Okay, so you can check the edges, so edges of your bandpass output and edges of the DFT output. So each and every edges the out signal will functioning. Okay, and so this DFT output given to the dynamic feature derivatives. Okay, okay, and finally we are come up with the MFCC output. Okay, so here you can analyze the MFCC output. Okay, so here this frequency range is minimum. Here the frequency range, it's a maximum one. Okay, so here we can plot it. Okay, okay, so this pattern also you can analyze it. So this code run at minimum level. Okay, you can run at maximum level also. Okay, so you can analyze MFC data and the input audio signal. Okay, wow. So another set of MFCC input 4, this is one. Okay, so you can analyze here. Okay, so this signal initially start with some noises. After that it will come up with the normal audio. Okay, same, the MFCC also initially provides some noises. Okay, as per the input, and it's come up with normal. Okay, so the next thing is synthesis part. Okay, so this code it's possible for synthesis in any tool. Okay, any FPGA. Okay, so here we have synthesized this code in ATIC 7 FPGA. Okay, so here you can analyze the post synthesis and post implementation. It will take minimum utilizations of logic sizes. Okay, so LUTs and flip-flops and IO bits. Okay, so here on chip you can check the dynamic power and static power. After that you can analyze the schematic. Okay, so here you can analyze the schematic. Okay, so here we are given the AHP signal is read data H ready. Okay, so here AHB signal we are not analyzed in the simulation, right? So here the final part AHB slave we have presented. Okay, so here you can analyze the AHB data. Okay, so here ready, sorry, read data, H ready, address write data, H write. Okay, and this is a state machine process. Okay, so here it's a multiple data mode. Okay, so here as per the address, okay, I have created a H write and H write data. Okay, so here you can analyze it anywhere. Okay, so if the ready equal to 0, we have stopped the write also. After that we will start the writing process. Okay, okay, you can analyze it. Okay, after that, yeah, you can analyze the RTL schematic. Okay, so here audio input given to the audio buffer. Okay, so this audio buffer is a register. It will create some delay part. Okay, and it will given to the preamplifiers. Preamplifiers will work as a buffer data with sampled previous value to current value subtractions. Okay, so here the 0.95 multiplication part we have used array multiplier. Okay, so this is array multiplier 8 cross 8. Okay, and okay, after this preamplifiers, the Hamming window. So this is completely filter. So instead of this filters we have used the array multipliers 8 cross 8. Okay, okay, so this is the added part. Okay, okay, and this Hamming output given to the real and imaginary. After that it will be given to the FFT. Okay, so this is a FFT architecture, splitter FFT core combiner. Instead of this FFT core we have used Radix 4 design architecture. Okay, Radix 4 butterfly architectures. So this is a butterfly architecture for Radix 4. Okay, okay, and the output of this FFT given to the MEL filter. So it would construct with already told you 8 FR filter. Okay, so the final addition we are take. So this is the final additions. Okay, so we are added the real and imaginary part here. Okay, and the final additions we are taken here. Okay, so this is a completely MEL filter based architecture. Okay, and this is a DFT architecture. Okay, DFT core. Okay, transposition DFT core and combiner of DFT, and this is an energy model. It's a multiplayer. Okay, and final thing is dynamic feature extraction. So it's a multiplier. It's also a multiplier, but we have do some boosting the power level technique also here. Okay, and AHB slave. Okay, so this is a AHB slave state machine. Okay, so here you can analyze it for H write data, write read address. Okay, so everything we have generated. Okay, that's it. Okay, and final thing, you can analyze a document. Okay, so here the proposed abstract, proposed architecture, comparisons, MFCC notes. Okay, preamplifiers notes, Hamming window notes, FFT, MEL filter. Okay, so DFT, energy, dynamic feature derivatives, AHP slave. Okay, and VLSI nodes. Okay, literature survey. Okay, and the output screenshots. Okay, and final references. Okay, thank you.